Thank you everyone for coming. The title of the talk is a little bit different from what's on the program, but this is much more in line with what we're going to be talking about. So using transport maps for data science, uncertainty quantification with MParT.jl. A colleague of mine said there ain't no party like MParT, and I like it. So my name is Daniel Sharp. I am a graduate student here at MIT doing uncertainty quantification in the UQ group. And up here, you're going to see a picture of what is a transport map. Now, this is going to be a pretty high-level presentation. You don't have to necessarily understand exactly the mechanics going on. What we have to understand is that we've got a banana-shaped pile of dirt on the left, a PDF, a probability density function. And we want to find some kind of function t to make that banana look like a Gaussian, like a hill. If you remember way back when you took your probability class, you probably saw Gaussians a million times, and the reason is it's one of the few distributions we really understand. And so if we find some kind of coupling from this banana to a Gaussian, we kind of understand what the behavior is of this very non-Gaussian, very weird distribution. So as a graduate student, As a graduate student, I think a lot about housing. I just signed a lease. And so there's a housing data set in mldatasets.jl that's about Boston housing. If you think about a realtor, and I promise this is relevant, if you think about a realtor, any reasonable realtor will be able to tell you based on how many rooms your house has, what the crime rate, what the pollution in the air, all these kinds of different factors, these data points, they can gather that and give you a price of your house. They think, if you go on Zillow, you can find a price of a house, your Zestimate is $400,000. And that's a really important question. When you list your house, you have to say, what am I going to list it for? But realistically, this is what a lot of people use. In finance and consultancy, they use linear regression, and they say, here's a point estimate. My house is worth $400,000. But we all know that that's not how housing works. That's not how you buy a house. There's some kind of uncertainty on that. Houses never go for what you list it for, pretty much. And there are questions that you need to answer. If someone puts in an offer for your house, they say $380,000. Is that a good offer? Is $400,000, is that a meaningful answer to your question of $380,000 offer, should I take it or leave it? No, we need some kind of understanding of how uncertain is this price? How much variability is there in the price behavior? And linear regressions and very simple extensions thereof aren't going to tell you this distribution. And that's kind of what I'm arguing, why we should be using something more powerful than just some random linear regression. So here's a scatter plot of all of these random variables that we're sampling. We're actually just caring about this last row or last column, and that's sampling, or that's graphically showing the joint marginals between the data points that we care about and the price of the house. If you note, those are not really great scatter plots. If you do any data science, any predictive data analytics, those look bad. You can't just throw a linear regression. But you can, clean the data. And still, though, if you just plot these points, on the y-axis is the housing price or some measure of it. On the x-axis, here is the distance to job hubs in Boston. On the right is, I'm blanking on it right now, but some kind of weird function. We get heteroscedastic noise, very non-linear relationship. We don't really understand how these are related. There could be some interconnection, interplay between these two variables and the price. There's all kinds of problems that you could be facing. And you don't really want to use linear regression with that. Additionally, you could say, well, why not just use a neural network or something of that ilk? And that can get the non-linearity for sure, but it's a little bit harder to capture the uncertainty on it. And you have to really think about it carefully. And MParT is a great tool that you can use for doing nonlinear analysis. So first, of course, you're going to, first, I guess we should probably get into transport maps. I said you take a banana and you kind of move it down, move it into the center, make it look like a Gaussian. And this is kind of what the action looks like. We take a bunch of samples, or maybe a density, and we train some kind of function. So once we put the samples through the function, we get a Gaussian sample. We get a hill. And once we get a hill, that's really nice. I mean, I think, right? It looks like it's really nice. I mean, who knows? But why bother? Why bother with this Gaussian nonsense? Well, this is about the most complicated math you're going to see here. If we have the data X, the stuff that we can actually measure X, and the response Y in a data analytic sense, so think about this as, you know, rooms in a house, the age of the house, something like that, as X, and Y is the price. We want something like the price given the data. We want the conditional distribution. And if we fix the X for some given house that has measurements X, we get a function of Y. We get a function that's fixed, that's just on one variable of Y, that takes a conditional distribution, we fixed X, and we push it forward into a standard normal, n0, 1. This is a pretty incredible thing. And the reason is, well, if we have the function evaluated that's from the conditional to the normal, we can just move it over to the other side. And we have very efficient, very reasonably stable numerics to do one-dimensional function inversion, where we just move it to the other side and we say, well, the f inverse of z, our normal variable, that takes z, the normal variable, and pushes it towards the conditional distribution. Suddenly, we're just generating out of thin air a conditional distribution, which is what we care a lot about in uncertainty. That's going to answer more questions for you than just a standard point estimate. You now have a distribution. What does this look like graphically? Well, everyone likes animations. I like animations. So let's suppose we care about x being -1. We want to see what is the distribution of y given that x is -1. What is the uncertainty we have on it? You know, this banana distribution is very non-Gaussian. It's very weirdly shaped, and it could be pretty hard to actually, get this slice, get this conditional. But using a transport map that we train just from samples, we can get it pretty easily. We generate a bunch of random samples from a normal, and we put it through the inverse of the map, and suddenly we have this magical result where we have magical, conditional distribution. It just lets you do this in a very efficient, nice way. So let's move back to this housing. Well, before we do that, I guess, MParT, what we talk about here, is just a really good tool to do this. It's very efficient. It's built on top of Kokkos for portability. It has bindings to Julia, but I was the one who made those, but it's also bound to Matlab, also to Python, intended for portability and efficiency, so that you can do larger transport map problems bigger than we've ever really, seen in the scenario that we're working on. So back to housing, we can actually use these. Well, yes. First, you want to kind of clean up your data, standard stuff that you would do using linear regression, using neural networks. It's boring stuff you'd learn in any kind of statistical learning class, and there's all kinds of stuff you can do, some boring code, but I'm going to skip over that and say, let's partition our stuff into training and testing. That's what everyone does. You have training samples you want to get your map trained on to make it look like a Gaussian, whatever that means. And you have testing just to see how it does on samples of houses it hasn't seen. Well, I'm not a big fan of putting code on the screen, but I like 8 lines of code. That's about my limit. And I think this does a really good job. We say, okay, we want a complexity 2 map. You can think about it as polynomials if you're used to that. We have quadratics basically approximating this map in different dimensions. This efficiently takes care of that with this second line says, okay, here's the total order, and then the next line, here is the basis that we're using. You don't really need to get involved in how that's constructed. We do it all for you. And we're going to take some map options. This is saying this is the basis we want to use. We think that the data kind of lives where a Gaussian would between -2 and 2. And then we just create a map. Now, this is an untrained map, but this create component creates the T that I showed you before. It tells you, okay, here is something that maps a bunch of dimensions, your data jointly with, at the end, your output, your quantity of interest, your housing price. We map that to a one-dimensional Gaussian using this create component. And then the second box just says, okay, let's create the objective. We have training and testing samples. Let's test it. Let's see how it does. Let's train it and get a map. Here we show that the training error is 0.2. You can't really interpret that, but it's just an optimization function. But it's trained in less than half of a second. I mean, this is a really quick algorithm. We can train it on much more. I mean, I've trained it on 1,000, 10,000, 20,000, 50,000 samples in, less than a minute. And it does phenomenally well. And this is much more scalable than previous algorithms and really previous implementations of these algorithms before. So 0.2 isn't super interpretable, but the great thing about these transport maps is that there are ways to interpret them. We have rigorous ways. We have qualitative ways. We can look at the histogram and see that looks pretty Gaussian on the test samples. This map hasn't seen these samples before. It somehow moves everything towards a Gaussian, and it's all nice and good. We can also do rigorous quantitative measures. So if you're a probabilist, you'll say, okay, we should use the Kolmogorov-Smirnov statistic to measure Gaussianity. And that works great in one dimension, so why not? We can say that the KS statistic here is just about 0.05. That's pretty good. It's not perfect. Ideally it would be 0 or, ideally it would be 0, but nothing is ever perfectly Gaussian. And we've just learned from 460 samples. It's a pretty small data set, all things considered. And we do reasonably well. But what does that mean for me as the data analyst, as the uncertainty quantifier? Well, the nice thing is we can do approximations of conditional expectations, which is exactly what linear regression does. And so here, I show here's our linear regression, super simple, just multiple dimensions going to 1. And we do a one-dimensional Gaussian quadrature approximation of the conditional expectation. What that means is you evaluate 1 point and that's it. That's all you got to do. For each sample, you just evaluate for the fixed sample data, x, you evaluate the t inverse at 0. And if you want to see a plot what this looks like, I'm comparing just multilinear regression to my transport map. And I'm using an ML data set that's kind of meant to be reasonable for linear regression, to train and see how your model does against others. And so linear regression does pretty well. I'm not going to sugarcoat it. I'm not going to say that we're infinitely better. But what's really interesting is that, especially for the non-Gaussian behavior, and this is the bottom right too, for those, you see that the linear regression has a little bit of trouble with heteroscedastic noise, with noise that varies in the x component. It has a little bit of trouble on certain boundaries or something like that, but it does pretty well, and that's great. But if you wanted a point estimate, you wouldn't come to me. You'd probably use some kind of great neural network framework. We're at Julia. There's plenty of cool neural networks out there. What I'm trying to convince you of is that a point estimate isn't enough. A point estimate is something that won't show us what we really need. A point estimate can't really beat this, where you can take a sample, what we actually observe in the yellow, we can see where it lies on the distribution. So for a house 31, we see that the actual price of the house is pretty low, given its location, given its number of rooms, given its age, etc. Sample 13 is kind of exactly where we expect it to. Now, these kind of look Gaussian, and they look Gaussian, but we wouldn't know that. When we do linear regression, we assume Gaussian error from the linear regression. We just assume that. And that's basically saying we're doing an approximate model and we're solving that exactly. Here, transport maps are exact in theory. We're taking an exact model and solving it approximately. And so we didn't have to assume that it was Gaussian. This could be multimodal, this could be all kinds of distributions, but it just happens to kind of look like a bell curve, and it fits with our assumptions. You saw that the linear regression worked well, so you kind of assume that the error looks pretty Gaussian, and that kind of lines up. But being able to quantify this error, not having to make that assumption, is very powerful. If you only have a density, we have you covered. I only have so much time. I wish I could get more in depth with everything that MParT could do, but we can still approximate unnormalized densities. And not only that, like before, we can actually generate samples. So here is, I think, like 50,000 samples I generated from an unknown, unnormalized distribution. And we do pretty well. I'm kind of running low on time, But I'll try to get through the rest and say, well, what if I don't know how much approximation power I need? What I mean by that is I said at some point, here's a quadratic map, but you don't necessarily know things are quadratic or linear. And there are algorithms to actually adaptively choose that. And this is a very nice strength of the parameterization we use. Everything's kind of based on very well understood function approximation tools, polynomials, quadrature, et cetera. And being able to do that basically means, well, we can use tools that have been established in the community that are going to converge to some limit. We have some idea of how this behaves. It's explainable, it's understandable, and it's adaptable. So here I have an example where we use the adaptive transport map algorithm introduced by Ricardo Baptista, now of Caltech. And we are able to adaptively construct a map. In this case, I think this gets 19 terms, 19 parameters, okay? It's a very low complexity map, 19 parameters compared to our previous one, the quadratic one had 36 terms. But we can get a KS statistic in this case, and I regret to say that I forgot to, I accidentally deleted the histogram, so you don't see it, but the KS statistic is 0.06, so it's pretty close to what we had before it. The push forward on the unseen samples is pretty Gaussian, but we've demolished our complexity. We've cut our complexity of our map in half almost by just using things that exploit the structure of the problem, that take the samples and learn from them. And you don't have to understand any of this, and that's really the great thing about it. You can just be a data analyst and say, I want an adaptive transport map. I want to train my map adaptively. And you say, train map adaptive. Here is what I think is a good place to start, mset ATM. That's just, you can see the documentation on it for that. Here is the objective. Here are the options. Go run with it. Give me a map back. And that kind of time that you save from hyperparameter tuning is phenomenal. You don't have to worry about that kind of stuff. The kind of time that you save from not having to wait for very slow different models to train is great. That kind of time that the kind of information you gain from being able to quantify uncertainty is really good. And having this all in a high level language like Julia and also Python and Matlab is really great for actual problems. People actually use this. One of my collaborators on this uses it now in industry for power price forecasting. You can use it in academia. The previous example on the densities was from biology, estimating parameters for a biological model. And we have all kinds of great examples. I think we have 5 in Julia. There's like 6, but one of them is a little touchy. And so it's very well documented. I'm trying to make sure that it's even better documented. It's very efficient. We have all kinds of gradients, Jacobian vector products. We have, for different use cases, you need the log determinant of the Jacobian for the transport map. We expose all these things so you can, if you have something where you don't trust me to train your map, you can use your own optimizer. You can use Julia's built-in optimizers, even though it's in C++. There is no AD before you ask about that, just because it's in C++, it's hard to propagate. But we have robust and efficient suites of software for low-level things like polynomials, and if you've ever worked in multidimensional function approximation, multi-indices are exposed pretty well. There are affine maps. There are efficient evaluations for compositions of maps. So if you want to do something that's kind of like a deep transport map where you just kind of continually try to iterate over it, there's very efficient implementations of that. It's not perfect. There's stuff that I need to work on. Others, are helping me on. The inversion that I keep talking about is sensitive to outliers. It's sensitive to different, weird quirks of the data. The error handling is kind of tricky because it is a wrapped C++ library. We're working on that. I think it's mostly fixed now. This ATM adaptive algorithm could be better. It's a little fragile, but yeah, we're doing, going forward, making this a really important tool in uncertainty. We're making this for, we're going to squash bugs. We had at some point GPU compatibility, and that was lost for a little bit, and so that's kind of the next step. implementing all kinds of new cool tools and methods that people like you can use in predictive data analytics, or even academia, Bayesian inference, all kinds of things. And so I'd like to finish by thanking my collaborators, primarily Matthew Parnot, who wrote a major part of this library, as well as all the people listed here from the uncertainty quantification group who have helped me, mentored me, and given me advice on this, and my advisor, Yusuf Marzouk. Thank you, and I'd appreciate any questions that you have. Yeah.
So one thing I see is that this can have a very powerful urban planning application. Where, say, for example, if you're planning a new subway extension, a new metro extension, and you want to map out how we're going to have people moving along it efficiently, you can maybe use MParT. Is that a correct application in this case for MParT?
Yeah, thank you for the question. Sure. So the really nice thing about this is that it's really application agnostic. Anytime you want to get some idea of a conditional probability, anytime, if you think about linear regression, this can be kind of plugged and played, but have some idea about the uncertainty. So the short answer is yes, because as long as you have some kind of model to talk about your application, then you can use a transport map, really.
Final question, any assumptions that need to be held for the model to work correctly?
Unfortunately, yes. Measured transport is provably not good for point masses. And what that means is if you're trying to estimate rainfall, for example, there is a very large chance that no rain will happen in a day. And so that's like a sizable thing. You can't have negative rain, but you can have zero rain. And if you have that, then it's like trying to approximate like a discontinuous function with a line. I mean, it would be very difficult and actually just kind of impossible in practice.
Any other questions? Yes, I'll come on to you.
Hi, great presentation. So I know you sort of went over the implementation of the algorithm on a higher level, but how do compositions of maps work very efficiently?
So I think sorry, the next one we'll say the question, I'll have the presenter repeat it.
Yeah, so if you think about it, the way that it works is actually quite like a reverse mode automatic differentiation, if you can believe it. So you have, if you think about a composition of two functions, when you do a derivative of that or an inversion, it's basically you do it one step at a time and kind of do maybe like a chain rule. And so the same algorithms apply, reverse mode checkpointing algorithm. I forget the name of the people who made it, but that you can use. Inversion is just a sequence of inversions now. So like it can only be so efficient, but we do it in a way that really tries to exploit the structure of the problem without doing it, in a very silly way, if I may be frank. Thank you. And then, did you have a question? Just shout it and I'll repeat. Yeah, so I'm glad you asked that. The neat thing is I'm not actually doing optimal transport. Optimal transport is a really hard problem, and it doesn't really, if you notice, I never say anything about an actual cost function. There's a loss function you have to train, but an optimal transport is basically constrained optimization. You have to couple these two measures. This is just saying, okay, we want to fit the measure, but we don't really care about making it efficient. And what we sacrifice that, but in return, we get computational efficiency. And more important than that, we get this conditional problem. So, this is the training, but basically, this is what's called a triangular transport map, and that's what we use under the hood. And that lets us do the inversion. Sinkhorn you can't like take two parameters very easily and then invert the transport map for one of them, fix one, and it's difficult. It's a really good algorithm for what it does, but it's not an algorithm solving what we want to solve. So in return for suboptimality, we get a very good transport map that maybe maybe doesn't have a huge amount of movement in the measure, but we couple them in a computationally efficient way. Yeah, it seems I'm out of time, so out of respect for my following presenter, I'd be happy to take any other questions that you have afterwards.